Morning, boys and girls. We're out here today to check out refraction of waves. You guys might remember from previous learning that we've looked at refraction of light, like the bending of light as it goes from one medium into another. Light's just a wave, right? And so it makes sense that we might expect to see the same thing with like water waves. And so looking at this, deep water, it turns out the waves go a wee bit faster than they do in shallow water. And so we're going to have a look at what might happen when we have waves going from deep water into shallow water. To understand this diagram here, looking at this, those lines, the blue lines, they're like the wave crests. And the distance between each wave crest, that's called a wavelength. We use the symbol lambda for that. So this is wavelength in the first medium, lambda 1 measured in meters. And the red arrow, that's the direction of wave travel. That's the wave direction travel arrow. We can use propagation to mean like travel, wave speed. And so what happens is the waves go from a fast medium into a slow one. It's the same thing that happens to cars as they go from a fast speed zone into a slow speed zone, like going from the 100 k's an hour outside of Takaka, 50 k's an hour inside of Takaka. You notice that all of the cars must get closer together as they slow down. The time between them passing the 50 k sign is the same as the time between them when they're in the 100 k zone, or the time between them if in the 50 k zone, but because they're travelling slower, the distance between them must reduce. Same with the waves. The distance between the waves in the slow water is going to have to be less than the distance between them in the fast water. The only way that we can let that happen is if the waves bend. And so in the slow water, they're going to be closer together. Let's have a go at drawing what that might look like. Look, by bending them like that, we've made the waves be closer together. We've made that lambda 2 in meters. Lambda 2 is less than lambda 1 because V2 is less than V1. And so now what direction are those waves going in? Look at this. That direction of wave travel has bent as well. And we can use the same maths to work out how much that direction of wave travel has bent by as what we used for our refraction of light. Start by putting on a normal line at right angles to the boundary between the two different media. We've got a theta I and a theta R, just like before, but the maths for this situation, it's a little bit different. You might remember that we used N1 sine theta I is N2 sine theta R. It's a little bit different when we come to do the same thing with waves. V2 sine theta I is V1 sine theta R. And the reason for the swapping round of the V2 and the V1, why are they on different sides? That's just a consequence of the maths that we've got. We know that lambda 1 over lambda 2 is V1 over V2 is N2 over N1. That's on your formula sheet, and so that should prompt you to remember that when we come to do this calculation with V, we got to remember that it's the other way up. That one there, it's not on your formula sheet. You've got the N1 sine theta I equals N2 sine theta R. You got to work that one out. Right, so here's an example for you to have a go at. We've got waves in the deep water, 3 meters per second, coming in at this angle here, going into the shallow water, moving at 1 meter per second. I'm going to put an angle on there of 30 degrees. Pause the video, have a go at it. I want you to calculate the angle of refraction, draw on the refracted direction of wave travel and those new wave fronts. And remember that we've gone from fast to slow. We're expecting those waves to go closer together. Have a go. A quick calculation reveals 9.6 degrees. Let's draw that on, see if it makes sense, shall we? .6, smaller than 30, so it's closer to the normal. Something like that. Then we're going to have a go at drawing on our refracted wave fronts and just see whether or not they really do move closer to each other. One of the key things to remember when drawing on these refracted wave fronts is that they're always at right angles to the direction of wave propagation, like that. So if we draw them on, they have to be continuous. They have to join on, look, and be at right angles. So look, by drawing them like that, we can see that, yep, it's definitely at right angles to the direction of wave propagation, and look, it's closer together, much closer together. It should be 1/3 of the distance. That wavelength there, the long one, should be 3 times that short wavelength there.